All right, so today we're going to go over the recursion a little bit. Okay. So first off, I guess, why don't we start with a little bit recursion stuff here? All right. So first of all, include bits dash C++ std C++ period H. Here we go. And for instance, let's create a very simple recursion method, such as probably like a Fibonacci sequence, right? Okay, so for instance, we could have a void method here, FIB, all right? And then what we need to do is simply pass a starting point here, and that can be simply just x, right? Okay. And then, so recursion, so first of all, and define the stop case, right? So simply means where we want this program to stop. I guess in order to do that is basically a if statement, right? And then else, and we do some other logic here. I guess whenever the passing whatever the stuff, it is going to be equals to 1 and or x equals 0, right? And we simply just return something, right? I guess probably. The reason why it is because based on the Fibonacci sequence, right? So such as Fn, okay, Fn, the equation is n minus 1 and a plus n minus 2, right? Okay, and we do have some like a basic case. So because we defined, all right, so f0 to be 1, okay, to be 1 and to be 1, right? Okay, and we also define f1 to be 1. So therefore, we could use this formula, right? Okay. Therefore, f2 equals f0, right? f1 plus f0, and that is basically 1 plus 1. And therefore, we can use the previous case to solve f3. So f3 is basically f2 and plus f1, and then plus f1, right? And plus f1. So we simply borrow previous results here, and then and plus 1, right? And the plus 1, and then we have 3 here. So therefore, it is very important to define the basic case, or simply you can call that a stop case, right? Where the algorithm stop, or where it starts. That means simply whether f equals 1 or x equals 0, and we return 1. And in the else statement is basically this number is not 1 or 0, right? And for this part, you could also have is less than equals to 1. It also works as well. So there are many different ways to define that Fibonacci sequence here. And right here, so, and then we need to do what? And then we're going to have the FB of x, right? And then we're going to redefine that. So this one is going to be FIB, and this is x minus 1, and then plus FIB and x minus 2, right? Okay. And until it is 1, and then this algorithm stops. So overall, this recursion just well, it's just a simple math here, right? Okay. It's like find something and until it fails here. Okay. And then we also have something other stuff like, okay, so using recursion to simulate, or not to simulate, to achieve iteration process, right? Uh, Originally, right? So for instance, I'm going to call that iteration, okay, method. All right. For instance, we want to have a starting point and an end point here, and the for loop here, right? I starts at A, and I less than B. That means stops at the B point, but not included, and I increments, and then C out, right? Okay, so C out right here. What we could do is just simply print out I here, right? But these are very simple iterations here. And all you need to do is just call this method here and pass the starting point, such as 1 to 11, right? And then simply run this code. So this should be no problem for you. And then, oh, wait a second, we have return. Oh, this one must be integer return data type. Oh, wait a second. What is that? Uh, the iteration left operator, this is X. Okay, I'll just first off, I'll simply just comment this part. Okay. For this iteration method here, right? Okay. And by doing that, we simply print out the value of I. Okay, for some reason, yes. And how would we? Okay, next one is how would we use recursion to handle iteration process. All right. So we still use a voice method here, but we call that a recur method here. And we still need to have like a starting point here, right? And then something like that. Okay. And then we also need to have an if, right? And then else, and then we do something else here. So that means this is starting point, right? And this is the end point. So, okay, if A is not equals to B, right? Okay, that means this is 0, this is 12, they're not equal. So right here, so we are going to increase the value of A, right? Okay. And then else that means, okay, A is at B. Therefore, stop the algorithms here, right? Okay. And therefore, right here, and logically speaking, we need to A++, right? Okay. So we have to keep making it work, right? But for these, right, we also need to call this method again, right? So this is a method. And right here is A. And a B, I guess, is just the same value here, right? And in terms of that, I guess we can simply just call the maybe A here, right? So in the first turn is a 0. And the next round it increase. And else this one here, I guess we just return, right? Okay. So therefore, we can use recursion to manipulate iterations methods here, right? Okay. And until it reach out to B, right? Okay, so therefore, this one in the line, and I'm going to call recur method here. I'm going to pass a number here and then right here, and then let's give it a go here. Okay, I need a semicolon here. Run this code one more time. As you can see, so this method will be called every times, right, until it ends. So basically, all right, before iteration invented, so yeah, programmer were using recursion to handle the iterations here, right? As you can see, so these will do exactly the same job here. And I can also put the print method after A++, right? Okay, that means we'll show the result after A's value being iterated, right? So therefore, we can have a different result here. So absolutely, all right. So as you can see, iteration and a recursion, they're different, but they handle the same result, right? Okay, so, but I guess I need to change that into less than, right? Okay, therefore, I can have a real, so for this one, I think I need to change this one into 0, and then it should print exactly the same result here. It's from 0 to 10, right? Exactly the same results here. All right, okay. So I'm going to update these two samples here, right? Okay, there we go. I think I'm going to use lead code to render the format. Okay. Here we go. Yeah. All right. Okay. Well, I'm going to also forward these two codes to you, and then let's see. Okay, where's chat? Chat is here. Good. Okay. Do you have any questions in terms of how to use recursion to handle iteration process?
No.
Good. Okay. Um, and then, okay, so now what we could do is let's dive into the DFS here. All right. Okay. We do have the textbook here, and let's see the graph theories here. Okay. The graph theory. All right. Okay, this is chapter 11, basic of graphs. Many programming problems can be solved by modeling the problem as a graph problem and using an appropriate graph algorithm. A typical example of a graph is a network of rows and cities in a country. Sometimes, though, the graph is hidden in the problem and it may be difficult to detect it. This part of the book discusses graph algorithms, especially focusing on topics that are important in competitive programming. In this chapter, we go through concepts related to graphs and study different ways to represent graphs in algorithms here. So first off, okay, the graph terminology. A graph consists of nodes and edges. In this book, the variable n denotes the number of nodes in a graph, and the variables m denotes the number of edges. The nodes are numbered using integers 1, 2, and n. For example, the following graph consists of 5 nodes and 7 edges here. 1, 2, 3, 4, 5. So now why we need to use recursion to solve this kind of a problem, all right? Okay, so first off, let's see. Okay, where is the annotations here? Okay, so the recursion is like you're using a method, whatever, okay? And the X is basically the node itself, right? And a node has 3 branches here, right? Okay, and then we're checking if this one the next branch, the node is not nil, right? If it's not nil, that means, or not null, that means there is. So we're going to work on this path. So every time the program could only pick one path to go. So therefore, in the first round, we pick this one. And then and in this node, this one has 2 branches, right? It doesn't really matter which one we pick, all right? But we just pick one of those. And suppose we pick this one. So 5 has only 1, so we traverse this one here, all right? We traverse this one, and this one has 1, 2, and 3. But this one, we have already checked this one, right? So we do not pick this, and therefore we pick that. However, we traverse this one already because this is a starting point, so we do not pick this road, but we pick this one. And eventually, all right, we traverse everything. So this is a recursion, all right? So that's why we need to use a recursion algorithm mechanism to solve a graph problem here. All right, okay. And then let me do that again, all right? Let's see, all right. And it doesn't really matter which one we pick first. So suppose we pick 2 first, right? Okay. And if we also create a stack. So number 2 is in, right? And number 2 has 2 or 3 branches or 3 edges, right? It doesn't really matter which one we pick which one. So suppose we pick this road, right? Okay. And since 1 it has not been seen yet, right? So we put a 1 in. Now this one is checked. And then 1 has 1, 2, and also 3. But this one is where we started at, right? So we do not check. And then again, it doesn't really matter which one we pick. So suppose we pick 4, right? And the 4 is not in the list, so we put 4 in, okay? And then we reach out at this point here. And again, so 4 has 1, 2, 3, right? And a 2 is in, so we do not go. And a 5, okay, 5 is not in, right? And we check 5 here. And we put a 5 here, right? Okay. And however, there's a 1 last here. So, and apparently the number of a checked node is not equal to the total numbers here, right? And then we just go backward as this point here. And then there's only 1, so we pick this one. And eventually we traverse everything here. So therefore, we have to use recursion to solve this problem because regular iteration wouldn't possibly work for these. Okay, so that's why a recursion method is a must in order to pass silver level here. All right, okay. And a path leads from node A to node B through edges of a graph. The length of a path is the number of edges in it. So for instance, okay, 1, 2, 3, 3, 2, 4, 4, 2, 5. Okay, there we go. This one should be quite easy to understand. Okay. Next one is a path is a cycle if the first and last node is the same. So for example, the above graph contains a cycle 1, 3, 4, 1. All right, so this is a cycle. A path is simple if each node appears at most once in the path. All right, okay. And we have connectivities here. A graph is connected, all right, if there is a path between any two nodes. For example, the following graph is connected. 1, 2, 4, and a 3. All right, okay. The following graph is not connected because it is not possible to get from node 4 to any other node. For instance, but in USACO, usually you wouldn't be seeing a non-connected. All right, most likely it's going to be connected. The connected parts of a graph is called components. For example, the following graph contains 3 components: 1, 2, 3, and 4, 5, 6, and 8. So this is also a graph. It's just a by itself. Okay, it's just a by itself. Okay. A tree is a connected graph that consists of n nodes and n minus 1 edges. There is a unique path between any 2 nodes of a tree. For example, the following graph is a tree. Okay, this is very important. So n nodes and n minus 1 edges. There are several USACO questions. Okay, as I mentioned before, there's a hidden, right? Okay, I remember there's or sometimes though the graph is hidden in the problem and it may be difficult to detect it. All right, and that's why you are here, because I'm going to show you how to uncover the mysteries here, right? There's a problem. So if I remember correct, no, I guess it's not. Maybe it is US Open. That is a silver. Bessie's interview. Maybe it's this one. Pending. Let me check. Oh, maybe no. Bessie is looking for unfortunate K and her hiring. If there are n cows applied, therefore the number is n. Oh, I don't think it is this one. December. Okay, let's check this out. Oh no, this one's no. January. Let's check it out. The cow probably is this one. Strictly greater than 1. Or maybe it's not this one. Let's check out the February. Okay. Targeted practice number 2. This is one. Oh, this one is also not. Okay, I guess probably it's the US Open, this one. There are just too many questions here. This interview. No, this is not. Okay, never mind. Okay, so there are some several stuffs. Okay, let's keep reading through these stuff here. So that simply means whenever you see, okay, the problem is anything has n-1 cases, that is going to be a tree. That is going to be a tree. Wait a second. I really want to find it. Okay, I remember that is okay. That is a Thomas. That's my current another students. We just went over that 1 month ago or something. Okay. The silver to gold level is this one. Um, Let me find. All right. Thomas, USACO. Never mind. Let's see. This one, no. Yeah, it has to be silver to gold. Crowd create, no. Okay, never mind. Okay. Yeah, just too many students. Couldn't remember which one's which. Okay. All right. So yeah, this is very important. Okay. So n-1 edges here. Okay. And there's just unique one. And 1, 2, 2, 1, 2, 3, 2, 2, 4, 2, 2, 5. Okay. Um, and then we have edge directions here. A graph is directed if the edges can be traversed in one direction only. For example, the following graph is directed. So 1, 2, 2, 2, 2, 4, 2, 2, 5, and 4, 2, 5, and 3, 2, 1. The above graph contains a path 3, 2, 1, 1, 2, 2, 2, 2, 5 from node 3 to node 5. But there is no path from node 5 to node 3. Okay. So this is directed edges. Okay. This one is with weighted graph. That means from node 1 to node 2, it takes 5 units. From node 1 to node 3, it takes 1 unit. In terms of USACO question, it's like, okay, so Farmer John has 1, 2, 3, 4, 5 barns, right? Okay. And whatever cows, right? Basic cow or LC wants to travel from barn 1 to barn 2, it takes 5, whatever the fuels, or like 5 miles away, right? And from 2 to 5, so barn 2 to barn 5 takes 7 miles away. And also it costs like probably maybe fuels or some energy stuff. But this is something you will be seeing in the USACO question, right? Okay. So weight simply means the cost, okay? Or can be time, can be speed, can also be distance, can also be like a amount of food, something, right? Okay. This is it. And then we have the length of a path is a weighted graph, is the sum of edge widths on the path. For example, the above graph, the length of path 1, 2, 5 is 12, and the length of path 1, 3, 4, 5 is 11. The later path is the shortest path from node 1 to node 5. Exactly. So it's like a distance problem, right? Okay. So for instance, problem John wants to find the shortest distance between the two or the whole farms, right? Okay, something like that. And we also have neighbors and degrees. Two nodes are neighbors or adjacent if there is an edge between them. The degree of a node is the number of its neighbors. For example, in the following graph, the neighbors of node 2 are 1, 4, and 5. So is the degree of 3. The sum of degrees in the graph is always 2m, where m is the number of edges. And it makes sense, right? Because I mean, 1 with a 2, right? Good. And because each edge increases the degree of exactly 2 nodes by 1. For this reason, the sum of degrees is always even. A graph is irregular if the degree of every node is a constant d. A graph is complete if the degree of every node is n minus 1. The graph contains all possible edges between the nodes. In directed graph, the in degree of a node is the number of edges that end at the node. And the out degree of a node is the number of edges that start at the node. For example, in the following graph, the in degree of node 2 is 2, and the out degree of node 2 is 1. All right, okay. Okay, and then I'm going to quickly use Python to give you some inspiration of a graph theories here. So first off, all right, we all know, okay, so node is a class. It is supposed to be a class here. And we're also going to define a method here, initializations. So first one is going to be self, and we could also assign some data such as value, okay, value, and of course next, okay, or something, yes. And then right here, self val is going to be val. For next, we can just keep it empty here, right? And then we create a node as a class now here. And we can create a node one equals node, okay? And we could add any value we want, such as maybe, let's say one, all right? And we're missing one. So next is basically we're going to point to the next pointers here. So for instance, node one equals node one. For this, we can just put it like a none, right? Because it doesn't have none. Okay, next, okay, I guess I need to redefine that class here and define init. And this is self val. I guess, do I really need to have a next? Maybe no. Okay, I just need a val here, and a self period of val equals val, and self.
think
Okay, I guess was that
I think none should be capitalized.
capitalized, right? Okay, so then yes. Oh yeah, there we go. Okay, that's good to catch over here. I think I'll just re-declare that, then define init and the self period of val. Yeah, I think I can have a next here. So I don't have to initialize it, but I can just keep it here. Yes. Okay, makes sense. Then node one equals node with one, and this is none, right? That is good. So node one, I can access is the val, which is one here, and the node one period next is basically, um, wait a sec. Am I able to do that? Okay, it doesn't have it. All right, never mind. So node two equals node this one, and the next one, I think so. Oh, let me have this one as none. All right, and then node one, I'm going to have a node one, and the next points to node two because I do have it, right? And then node one period of val is one, and the node one period next. I guess it points to node two here. Wait a sec. No attribute two. Okay, I guess I do need to, yeah, I guess I do need to declare that. Define this one here, and init self val val. This is the next pointer, right? Okay. And then, wait a second, never mind. So class node, define init, okay. Self val next, okay. And then self period of val is a val. And for this, I might do this one. Okay, so in the initialization, do I put anything here? I think I don't have to initialize it, right?
I
So
think you do.
I do, right? Okay. So for these, the next is going to be, can I put none here or put a node, something?
Self.next should just be next.
The next. Okay, yes.
Yeah.
I guess we have to. There we go, yes. node 1 is node, we just put a number. I'll put 2 here. Suppose this is the n. I would just, if it is a next, what is going to be the next data type here? I would say maybe just a none, okay? And the node 1, I can access it. Node 1 period next. It points to and node 1 period next. It points to empty. Okay, that makes sense. Node 2, and okay, it's a node, I'll just put 12. Okay, and then I wanted the next one is node 1. Okay, and then I guess these two are linked, right? So this val is this one, node 2 period next. This one will point to node 2 period next, will point to node 1. Okay, node 2 period next, the period val is going to be 2. Okay, so suppose we have a lot of, right? So, and then we create a nodes, and then we just save all the node 1 and node 2 inside, and then it becomes a linked node here, and we can traverse it and until the next one is null, is null or none. Then we stop that, and then we can traverse that. Yes. So in Python, it's just something like that. Okay, good. And then we keep working on that. So therefore, we have the colorings here. In colorings of a graph, each node is assigned a color so that no adjacent nodes have the same color here. A graph is a bipartite if it is possible to color it using two colors. It turns out that a graph is a bipartite exactly when it does not contain a cycle with an odd number of edges, for example, these. Okay, so basically, in silver level, this is all good, all right? So anything above is all good. So this one in the gold level, okay, you do need to um, um, polish and really master these. So therefore, I guess I'm going to just quickly skip this part. And this one is also good. Okay, and then we jump to the most important part, which is a graph representation. All right, before I dive into these, okay. So basically there are two ways to represent a graph. Is adjacent matrix and adjacent list. Okay, there are two ways to represent graph. First one is adjacency matrix. Second one is adjacency list. And this is the most popular, right? Okay, there we go. There are several ways to represent the graphs in algorithms here. The choice of a data structure depends on the size of the graph and the way algorithm processes it. Next, we will go through three common representations here. The first one is going to be adjacency list. And this is the most popular one. And each node X in the graph is assigned adjacency list, and that consists of nodes to which there is an edge from X. Adjacency lists are the most popular way to represent the graphs, and the most algorithms can be efficiently implemented using them. All right. And in C++, it's using vector. Okay, it's using vector. And in Java is array list. And in Python, it's just a list. Okay. Therefore, so this is the most common data structure you'll be using, which is a vector. Why we need to use a vector is because usually we don't know how many data over there. So we want to use a dynamic auto resizing mechanisms, and therefore it's a vector here. Okay. And for instance, the constant n is chosen so that all adjacency lists can be stored. For example, the graph 1, 2, 3, 4. So firstly, we have adjacency 1 and a pushback 2 here, right? And then we have 2 pushback 3 and a 3 pushback 4 and also 2 pushback 4 and the 4 pushback 1. So therefore, we can use these to traverse, right? Okay. Now this is how do we actually store the data. All right. Okay. Pretty straightforward. And therefore, okay, the proper data structure is a vector. Is okay. In C++, okay, in C++, it is vector. Okay. In Java, it is array list. And in Python, it's just a list. Okay. Yes. Okay. So which means it doesn't really matter which language you are using, but you gotta use vector, array list, and the list. Okay. And okay. And if a graph is undirected, it can be stored in a similar way, but each edge is added in both directions here. Okay, so therefore we have to use a pair to solve the problem. And then for a weighted graph, the structure can be extended as follows here. So we just use a pair because first of all, we need to know which node, and then we have to know, okay, the weight between the two nodes, right? Good. So therefore, again, it's a vector again. For instance, in this case, the adjacency list of a node A contains a pair V and a W. All right, W means weight. Always when there is an edge from node A to node B with weight W. And for example, the graph is just like that. 1 to 2 to the 3 and 4. And this is the wedge. Okay, this is the weight. This is the weight. All right. So therefore, if the problem has a weight like the distance or like a time or whatever speed, fuel, that is always going to be a weighted graph simply by using pair, and that should be all good. Okay. And then, all right, if the question contains travel cost, fuel, fuels, and what else? Maybe like such as time, okay, between two locations. So the two locations, uh, it is a very likely to be weighted graph algorithm related. So right here, the location can also mean the connection between two people, all right, such as communication, uh, gift, gift, redistribution, redistribute, gifts, redistribution, um, and yes, okay, and others, right? Okay. There was a questions. It is exactly gift redistribution. It's like a person A has a gift and send it to other people, right? Okay. And then other people is also redistribute the gift to anybody um, but A, right? Okay, so that means we just cut A from the equation. So yeah, so something like that. Okay, there we go. Therefore, this is weighted, and I can tell you, you'll be seeing, yes, you will be seeing this kind of a question in silver division. It is guaranteed. Yes, it is guaranteed. Okay. And it can be stored as follows: adjacency 1, okay, push back 2 and 5, 3 and 7, 4 and 6, 4 and 5, 1 and 2. Okay. And the benefit of using adjacency list is that we can efficiently find the nodes to which we can move from one given node through an edge. For example, the following loop goes through all nodes to which we can move one node as here. It's basically traversing. Okay, it's basically traversing here. Okay, good. So now this is the adjacency list. Okay, next one is going to be adjacency matrix representations here. An adjacency matrix is a two-dimensional array that indicates which edges the graph contains. We can efficiently check from an adjacency matrix if there is an edge between two nodes. The matrix can be stored as an array. Okay, so for instance, it's just as simple as that. Okay, where which each value adj a and b indicates whether the graph contains an edge from node A to node B. If the edge is included in the graph, then it's 1, and otherwise it's 0. For example, the given graph, for instance, like that. So the representation can be like that. So 1 to 1 is 0. 1 to 2 is 0. And 1 to 3 is 0. And 1 to 4 is 1. All right. Because I mean 4 to 1 is a match. And then, all right, so we have 1 to 2, there is. And a 1 to 3, there is no, because no direct connection. However, 2 to 3 is a 1. And a 3 to 4 is a 1. And then this is another way to have a representation, which is matrix. I guess it makes sense. It makes sense as well, right? Okay. And if it's a weighted, right? So for instance, it has a 5 and a 6. So I guess since 1 is to 2, right? I guess right here, we just change that into 1 and a 5 because, I mean, right? Okay. And then 2 to 6, 2 to 6, 2 to 3, right here. We just change that into 1 and 6, right? Okay. It's basically the same stuff. Okay, basically the same stuff here. Okay. And then if the graph is weighted, yes, exactly. The adjacency matrix representation can be extended so that the matrix contains the weight of the edge if the edge exists. Using this representation, the graph looks like something like that. All right. 1 to 2. Okay, 1 to 2 is a 5, right? And then 2 to 3 is a 7. Okay. And a 3 to 4 is a 5. And a 4 to 1 is 2. So by using this is okay. And you could also use the previous notation. That means there is a 1 and then is a 5 here. And then this one is 1 and a 7, right? Okay. But usually unless you understand this mechanism, you can just get rid of these and simply put a number here. So again, the key is, okay, if not equals to 0, then means there is an edge, right? Okay, so this is the key basically. All right. Okay, and the drawback of adjacency matrix representation is that the matrix contains n-squared elements, and usually most of them are 0. For this reason, the representation cannot be used if the graph is large, right? I mean, there are just too many redundant data here, right? So that's why it is not very popular. But it's easier to understand. It's a bit easier to represent. But the overall time complexity is usually pretty chunky and squared. So we usually don't use it unless it is a small size. All right, the data size is small, then we can use it. Okay. Uh, Therefore, okay. And when do we use? Okay. Okay, only if the data size n is small, we recommend to use adjacency matrix. All right, there we go. And the last one is going to be edge list representation. Yes, edge list contains all edges of a graph in some order. this is a convenient way to represent a graph. If an algorithm processes all edges of a graph and it is not needed to find edges, then it starts at a given node. The edge list can be stored in a vector, okay, such as that. Okay. And where each pair A and B denotes that there is an edge from node A to node B. Thus, the graph is just like this. Okay. Okay. Therefore, okay, usually our main tool is adjacency list. Is faster, better, and easier to use. Okay. And then chapter 12 is a graph traversal here. So the graph traversal, okay, our main character is a depth first search, and then another one is a breadth first search, BFS and a DFS. Both algorithms are given a starting node in the graph, and they visit all nodes that can be reached from the starting node. The differences in algorithms is the order in which they visit the nodes here. Okay, so I guess let's maybe check the algorithm first. Okay, as you can see, this is a recursion, right? Okay, so if visited this specific node is yes, then we return, and then we just assign that to be true, and we also have a for loop to run this recursion method here, right? So therefore, as you can see, in order to really understand the DFS, recursion and iteration is a combination, right? You have to really understand these two mechanisms as a whole, right? Okay. So this is recursion, the method called itself, and in a for loop, right? Okay. Okay, so that's why at the very beginning of this program, so I'm reviewed and go and went over the recursion first, and also compared with the iteration together. So for instance, this one here. And the first one, how will we use recursion to handle iteration process? Okay, and then using the iteration individually. And if we combine these two together, it is basically a DFS. Okay, all right. So this is going to be it. Okay, I guess. And then let's maybe go over a little bit of the breadth first search on this one here. So breadth first visits the nodes in an increasing order of their distance from the starting nodes. Thus, we can calculate the distance from the starting nodes to all other nodes using the breadth first search. However, breadth first search is more difficult to implement than depth first search. So therefore, in the most of the time, you wouldn't be seeing a lot of BFS algorithms in USACO, right? And then I'm going to show you some BFS problem, if I remember correctly. So the silver painting the fence post, this is the one, maybe. I don't think this is the one. The open contest, this is the previous one. Okay, let's see, maybe this is, okay, a barn tree. Okay, a barn tree. Okay, yeah, yes, this is, okay. Remember I mentioned the tree node, right? Okay, so there are n minus 1 rows. This is the hint. That means this is a binary tree. This is a binary tree problem here. So for instance, let us just, well, go back to the previous chapters here, connectivity. I remember I mentioned n minus 1 somewhere. Where is that? Adjit, the shortest. N minus 1, irregular. Wait a sec. Hold on. There are just too many stuff here. Wait a sec. Length, simple. Oh yeah, a tree is a connected graph that consists of n nodes and n minus 1 edges here, right? Okay. And this question. Farmer Jones has n barns numbered 1 to n, and there are n minus 1 rows. Yes, boom. That's the hint. That's the hint. You want to use a tree-related algorithm, right? Okay, there we go. So this is a very, very obvious hint. Okay. Um, uh, if I mean anyone who realized that could solve this problem super fast, okay, because it's n minus one rows. That means n minus one edges, right? Okay, there we go. Okay. So yes, this is experience. This is basically experience. If you did a lot, you can quickly verify. Okay, so this question is apparently it is a tree problem here, right? And of course, is the name is a barn tree, right? Okay, pretty good. And I'm going to post it here as well. Okay, this is a barn tree. Okay. Um, okay. So now, as you can see, this is how do you utilize this book, all right? Okay, so first of all, you got to finish all of the reading assignment. And then when we finish that, you are able to simply apply the knowledge to the real questions here, right? So for instance, when I see this question, right, I quickly verified, okay, this is a tree algorithms, graph algorithm stuff. Why? The reason is there are n minus one rows. What is road? Road is something connection, right? Connects one and a two, right? And that's an edge. Okay, that is a tree. There we go. Good. Okay. So now I'm going to, I guess I'm going to assign some homework for you. All right. So first of all, so please review chapter 11 and chapter 12. I guess that's it. And also review and please review the questions above, which is a barn tree, which is this one. I'll just put it here. All right, below, okay, below. And this is the barn tree. Okay. And there are also some lead code problem we could work on in the future. All right. So those are also graph theory stuff, but the most important stuff is uh, understanding the theoretical stuff, and then we can practice some questions. All right, good. Okay, I guess this is going to be everything for today's lesson, and I guess yes, a graph theory. Next class, I guess probably next week, we're going to work on more graph theory. And then, yes, okay, graph theory is very important. And you have to master graph theory. Otherwise, there's no way to pass USACO silver division. Okay, good. Do you have any questions? Good, perfect. Then I'll be seeing you next time. Okay, bye.
All right, bye. Thank you.
Sure.